the most vast and unimaginable scales. And tonight we'll hear some different stories about how CFEngine has been used in different scenarios. I think what's nice about that is that because there is an idea behind CFEngine that allows you to apply principles to the way that you manage systems, it doesn't really matter what kind of scale that you have. If you have an idea about how systems should be defined, the scale doesn't really matter. You can actually manage from the smallest to the largest, and it's exactly the same. So, without further ado, I want to introduce our speakers because they have a lot of interesting things to tell us. And the first one is Mike. Mike has been part of the CFEngine family for quite a while. Mike works at LinkedIn, and that deserves a clap. LinkedIn, it's this thing with, that thing, with the icon and the buttons. And excuse me, Mike's been pretty much involved in setting up the whole infrastructure at LinkedIn from the time when it was just hundreds of servers to when it's now tens of thousands of servers, and he'll tell you about the details. And he's the production automation architect for the last 4 years. And he's swanning off all over the world doing his so-called system administration from places in Hawaii, and we see these pictures of, living it up, the fine life. You see the tan? Yeah? This is how hard he works. And the point is that if you're using CFEngine, you don't have to work it out, right? So, it's a good story. So he's going to tell us about recent achievements of LinkedIn moving from CFEngine's class structure to an external system called Range. And he's going to tell you about all of these details. I don't want to preempt the talk in any way, but it's a huge privilege, Mike, for you to come all this way from Hawaii to this cold place where people work to tell us about these important things. Thank you so much. Please give it up for Mike.
Thank you for coming tonight. Really appreciate it. So, what do system administrators really need out of being able to answer questions from machines? Any typical day, you need to know what software is installed in your machines, and it could be 10,000 machines in a very case. Maybe you need to find a machine with an SSD installed with a specific serial number, or where a user has sudo access. Your questions from a sysadmin could be very broad. You often don't even really know ahead of time what you need to be able to answer. So how do you do this when you have 100,000 or 200,000 machines? And at scale, when you try to answer these questions, this becomes very difficult. The more machines you have, the more data you collect, it takes a lot more effort to be able to extract data out of this. The biggest need we had for this was actually pushing CFEngine changes ourselves. So if we were going to centralize NC services, for example, where was this file different across 50,000 machines? And that's a very hard question to answer because you basically have to perform an MD5 sum computation on this file before you centralize it. So what we wanted is we basically wanted a two-way configuration management system. We wanted to be able to use CFEngine to enforce whatever automation we wanted and enforce this golden image that we desired. But we also wanted to be able to communicate state from our machines back to a centralized place. I wanted to be able to collect any file, any remote command, any output from every machine. So typically what happens is management comes to the sysadmin and says, hey, I need some sort of question answered. And what happens typically is if you're at a small scale, you use some sort of variant of an SSH loop. Let's say I'm going to connect to 20 machines, execute a remote command, and gather this information back so I can parse it. If I need to query 1,000 machines, so maybe I'm using DSH or some alternative that does SSH in parallel. And really, if I get to a large scale, maybe I can push a CFEngine policy to make a reports statement based off of the class. But the CFEngine administrator is really the only person that can do that. If you can't push CFEngine policy, you can't do that. But at scale, SSH data collection really breaks down. If you have to connect to 50,000 machines to answer a question, firewalls are going to get in your way, network connections aren't going to happen, sockets time out. And plus, your sysadmins have Unix skills, right? They don't need to be doing really mundane data collection. So yeah, you missed data. SSH hangs, remote could have SSHD offline, firewalls get in the way. If you need to do something that requires root access, maybe sudo doesn't execute correctly, or you have some complex command sequence in your local shell that's hard to parse out. And then even if you're able to collect data from 50,000 machines, you have to be able to parse the data after you've collected it. And all of this can be very cost significant to do. If your manager asks this 3 or 5 times a day, or you just have to answer various questions before you push policy, your entire day could just be spent doing this data collection. So our first generation on this basically depended on rsync. So what we basically did is from our CFEngine client, which is basically our end node that's being managed, we executed an rsync command to transfer data back to our policy servers. And then our policy servers executed another rsync to centralize to a central machine. And this is kind of a diagram of how this worked. It was a 2-stage rsync process. Going back, this worked at small scale, but once we got to a decently sized scale, it started to break down. There's a lot of downsides to why this wasn't optimal. Basically, our clients were only sending data to a single policy server. If that policy server went down, we lost reporting from those machines. This was very small random I/O. So if for every machine I had to collect 100 files, and I had 10,000 clients, now I have 1 million files that I'm rsyncing around. And if I wanted to add a new object to centralize, if I had 10,000 clients, this is now 10,000 new files in the file system. And the downside to this is that it can only be queried from this central machine. You know, I had to have access to this one centralized host and be able to crawl this data. This is not really ideal. It basically covered us for the first few months, but it started breaking down on us. It became really difficult for us to crawl this data. So we had 30 policy servers executing rsync commands every 15 minutes, trying to shove everything into this one box. The disks on this machine were at 100% utilization, just trying to keep up with the rsync data transfers. If you actually had to crawl this data, it took about 30 minutes with a find and a grep to just answer a basic question. And then rsync started piling up. So every 15 minutes or so, we would execute a transfer, and then the previous 15-minute transfer hadn't completed before the next one kicked off. So this obviously was just breaking down in scale. Our data set was not really large. Let's say we had 10,000 machines. There's only 8 to 10 gigs of data that we needed to collect. So the total size of our working set is small, but there are millions of objects that we need to collect. Only our team of system admins had access to the centralized machine, so no one in the company really, they pretty much had to file a ticket. So the process didn't change from before, but instead of SSHing the machines, we were just crawling this rsync data. And then the more we searched it, of course, the more I/O we generated, the more this slowed down, and rsync couldn't keep up. So this didn't scale. Also, we had this problem with garbage collection. So if we re-imaged a machine or a host died or wasn't coming back, was being decommissioned, these files remained on the file system. So we had to basically do a garbage collection of every day of deleting files older than a day And so then rsync had to transfer new files, and it was even more work for rsync. So garbage collection became a very big problem. So what do we want? Anyone at LinkedIn should be able to ask any question about our infrastructure in real time. We should be able to return data from hundreds of thousands of machines in seconds. We can pick any file off the file system that users would want to be able to query, or any remote command execution. So there's kind of this debate going on right now in automation: is remote command execution, immediate remote command execution, valuable? And using this, I would argue it's not, because what we're able to do here is we're able to execute commands that people would be interested in on a regular basis, provided into the system that can be queried. And that's really what people want with remote command execution. They want to be able to query the state of machines. In this tool, we should be able to query scope. So I should be able to just know about my local machines. I want to be able to query machines from an entire data center, or I want to be able to query machines from all data centers. And I want to make this easy to parse. So sysadmins are used to using grep, set, awk, cut, paste, whatever. So we should be able to put the host name in front of every single line that gets returned, so it's easy to count instances that we find of the machine. And we'll see this in a little bit. And being able to query this from anywhere on the LinkedIn network allows us to build higher level automation tools on top of this. So if we populate DMI decode into this, now our CMDB can get the contents of DMI decode from all of our machines, and was actually able to modify our CMDB based off of discovered hardware on the machine. So how can we scale this? In the diagram we saw before, where there was a single centralized host, we really don't need that. We just need to be able to query all of our master policy servers for its view of the world. What does it know about its clients? Because data is sharded at that level. So if we have 30 policy servers serving all of our infrastructure, if we query all 30 policy servers, we get the complete working set. We have a lot more computing resources at this scale. We have a lot more network, CPU, and we have a lot more failover as well. So this garbage collection problem we had, we're going to hold all of these objects in RAM, and we're going to put a time to live of 60 minutes on it. So since the working set is fairly small, it's only 10 gigs, this is easily sharded over 30 policy servers. And we're going to avoid disk I/O. So we don't ever have to worry about this garbage collection problem again. So if a machine dies and goes offline, in 60 minutes it falls out of the cache, and it doesn't exist until it comes back online and CFEngine starts executing on it again. So the question is how can we trust this? How is this reliable? And we end up having to trust our CMDB. So our CMDB knows what host should be online and what host should be there. This system shows the live state of what's actually online now. So our on-call pager basically every morning gets a list of machines that are no longer reporting to the system, which should be online. And this just becomes a daily part of how we recover machines. A key point of this, at LinkedIn, we use multiple policy servers per cage. And we do this so we send data into each policy server. And the reason why we do this is we can use load balancing here, and we have failover. And I'll get to this in a moment. If we send our data to 4 policy servers and we query the first policy server and it's not online, we have 3 other servers that we can fall back to. So this is our cache. It's extremely simple. It is basically a Python dictionary object. This at the top is basically the key, which is host 12345 at CFEngine.com, separated by a pound and then the file name. So this is basically a key entry in the cache, and the value is a simple array. So array sub 0 is the contents of the file. MD5 sum, OS stat, and word count. These are the objects that we're basically most interested about as far as working with this data. So every key in the cache is unique, basically using the host name and file name. Your computation power is on your end nodes. That's where you have hundreds of thousands of CPU's cores. So if you have to do something like MD5 generation, it makes sense to do it on your clients instead of doing this when you try to extract the data. So what we've done is we try to populate as much metadata about this command or this file that we can. So on extraction, it's very easy just to look at the MD5 sum, and it's just a string comparison to see what files are unique or not. We just use these 4 items. If there's any other metadata that you could possibly think of about your files, then extending this is trivial. So this is a very basic graphic, but this is what happens in one of our CFEngine policies. We have a directory called var CFEngine outgoing that we just symlink objects into. So we could symlink the entire etc sysconfig directory, and when this policy executes, it basically inserts every file in those symlinks into all of our 4 policy servers, which now can be queried. So now that we talked about how we insert data, how do we extract it? Again, scope is a very critical concept for this tool. I just want to query machines in my cage, I want to query the entire data center, or I want to query all data center. We need to find a randomized policy server from each level in the scope. And when we do, we basically need to test that Redis is responding to our policy server, and if it does, then we can query it. For each policy server, basically search Redis and see if we can match objects based off of a string, and then figure out what type of extraction we want to do. So our first example, we'll look at local scope extraction. This is basically the default behavior of the utility. We're only going to query a single policy server. It's the least amount of data. But we decided to use this as the default behavior of the utility because there's kind of a learning curve for the company here. The company has to learn what data exists in the cache. They need to know what files are there, what commands are being executed. And the only way that they're going to really learn how to use this is by playing with the tool. So we don't want to pound our infrastructure if it's just not garbage data being returned. So this is kind of a graphical image of what's happening. If this is a theoretical data center, these lines are basically separated cages. So our first 4 policy servers up there, we're this querying machine in this white circle, and we just picked one of the 4 policy servers at random. If this policy server in red didn't respond, we would just pick another one at random until we got a response from one of them. And this is basically our utility executing. This is probably hard to see if it's hard to read, but the very last line of this utility is basically stating, in this data center, I've picked a random policy server and it pushed it onto this list after it tested a Redis connection. So site scope, pretty much the same thing that we saw before, but instead of doing it in one cage, we're going to replicate it to all 3 cages. The amount of data that returned is directly related to the size of the data center. So if your data center only has 10 nodes, of course there won't be much there. If it's 10,000 nodes, it's quite big. This could be cross-country traffic. So some of the examples we'll see later will extract the entire cache from Atlanta to Sunnyvale. This is pretty useful for LinkedIn when they're trying to find differences within the same application group. So all of the web servers in LA or all of the web servers in Chicago, how are they similar to each other? And this drives multiple policy servers per data center. And this is just kind of a graphical example, 3 cages. Again, we picked policy servers at random to build our complete working set. And this is kind of the utility in action. I know it's impossible to read. But the very bottom line is basically picking a random policy server from each cage. Our global scope, query one policy server from every cage of every data center. The amount of data that gets returned here is quite a bit. This is a lot of network overhead, but these are the questions that people generally want answered. Where have we experienced hardware failure in the past hour? Or what version of CFEngine is installed on all of our machines? And this is kind of the idea. These long lines would basically be walls between data centers that are 3,000 miles away. But I hope this kind of conveys the idea of we have multiple cages per data center and multiple data centers. We just have to pick a policy server from each cage. And this is our utility executing, and at the very bottom down there, it's picked about 30 policy servers to build this working set. So there's no reason why this couldn't be multi-threaded. If we have to query 60 policy servers to extract this data, we're doing the same exact operation on all of our policy servers, so become multi-threaded. There's two places where being multi-threaded here helps. When we search for keys, basically to figuring out where these objects are that we need to extract, and the actual data extraction itself. So the way Redis finds keys, it's basically built in, and the reason why we use Redis instead of Memcache is Memcache is a very simple key value store. Redis provides some additional objects on top of just being a simple key value store. It supports lists, dictionaries, sets, and common operations. So one of these common operations is the keys command, and it supports globs. So in this command at the very bottom, I said extract sysops cache, search nps *cm.conf, and we just returned 4 machines that matched nps-star.nps-cm.conf. But this is basically how we're searching for objects in the cache. And then Redis has this idea of pipelines. And what a pipeline is if I'm about to extract 1,000 objects from a policy server, I don't need to do back and forth communication. I can queue up a single command to the policy server that says, send me 1,000 cm.confs, and the policy server executes at once. So this is kind of like the best analogy is a large TCP sliding window. Instead of this back and forth communication, we can make a single request for 1,000 objects, and we get it satisfied immediately. So this is basically an example of performing a cache extraction using a pipeline object. So our query here is we're saying our scope is local, our string is nps-star.cm.conf, and md5 sum is true. So in our utility, contents, md5 sum, stat, and word count are just true-false flags. And depending on if they're true or not, depends on which element of the array we extract. So here we're extracting the md5 sum of cm.conf against 4 machines. When we execute, again, hard to read, but at the very bottom here, we're basically showing 4 cache objects and their md5 sums. And this is how we do CFEngine changes. So whenever we're about to make a change, we know exactly what machines are going to be affected before we do it. We use this utility to basically audit our environment to say, if I'm going to centralize Etsy services across 50,000 machines, and Etsy services is different in 4 places, do I need to preserve those changes with a class statement, or is this something that someone screwed around with and I can just override it? But we have a very high level of confidence before we push a change because we're doing this auditing. We also do this with like remote, you know, if people are submitting automation requests saying, I want to make sure HTTP remains online with the web servers, they can use this to basically audit our process table and confirm that automation is behaving as their request intended. So with this utility, compression is very significant. At first, we were just inserting data into this cache in plain text, but there's really no reason why we couldn't be compressed. So there's some advantages. Inserting into the cache, there's less network overhead. And yes, compression is CPU intensive, but this action is happening on your end nodes where you have hundreds of thousands of CPU cores. So this is really where your horsepower is. It's also a lot less network overhead when you're trying to pull data out of the cache. And since we're holding these objects into RAM on the policy servers, we just arbitrarily set a cap of 10 gigs for Redis to use, but it allows us to put more objects into the cache if we want. If there's less network overhead, if we can extract the same amount of data with less packets, this utility actually accelerates. It gets massively faster. And one thing that kind of surprised us is we expected CPU overhead to be a lot higher if a client had to decompress data. And what we found was the opposite. A single machine decompressing the entire cache was actually less CPU overhead because it was processing a lot less network packets to extract all of this data. And there was an added security benefit of now all of this stuff exists in the cache in binary form. A hacker obviously couldn't be able to tell that this is a bzipped piece of data, but a script kiddie just looking at a cache can modify it. And so we looked at 4 different compression algorithms compared to plain text to figure out what would be the best for us. And so this was basically how much time and CPU horsepower it took to insert for a single client into the cache. Plain text is at the bottom, and BZ2, which is another popular algorithm, which is what we ended up choosing. But this is basically the time and CPU required in order to compress this data. LZMA, of course, here is not doing well. This is CPU cycles, kind of similar to the previous graph. Plain text, of course, requires hardly nothing. BZ2 is a little bit more expensive, but not too much. And this is really a significant graph here. This is the size of the cache for our entire Atlanta data center. So it was just a little over 1.5 gigs in plain text form. In BZ2, it was like 300 meg. So the amount of network transfers here is pretty radical and it's being reduced. And this is the time to extract our entire cache from Atlanta to Sunnyvale. And this was significant for us. So using compression, basically the BZ2 was almost 300% faster being able to transfer this data across country. And if you can notice here, the user time was actually less than plain text as well by probably 10 seconds. So less CPU consumption on extraction. Within the same data center, so this is basically a host in our Atlanta data center extracting the whole cache. There was still some improvements, although it wasn't as massive as a cross-country data center cache extraction. So we built a tool called Extract sysops cache, and this is kind of the Swiss Army knife to interface with this. All of this utility does is import a Python object called cache extractor. Cache extractor is the one doing the actual work to query Redis, dump the contents, and this utility basically prints it out in pretty form. So a few things that we wanted it to do was we need to be able to search for strings. So using the search function, we could say search for cm.conf or list files that basically showed all of the unique objects in the cache. We need to be able to extract data using contents, which is primarily what this utility is used for. But if I'm only interested in seeing what Etsy password has the most entries, I can look at the word count object. And then we needed to be able to do comparisons. So if we're going to perform a CFEngine change, this is such a common thing for us that we're going to centralize Etsy services, and there's 5 different versions of Etsy services. We need to do a comparison of it. So we can either do a one-to-many comparison or a many-to-many comparison. But basically, if we have 5 different objects, there's, I can't do the math off the top of my head, but let's say there's 30 different comparisons happening. Basically, this utility will compare each unique object and try to find the differences. And this becomes our change management request. We can just copy and paste this utility directly into the ticket, and management knows exactly what our CFEngine change is going to do. So here's an example of the utility executing. So I execute this command, again it's hard to read, but extract sysops cache, we're searching for cm.conf, and we're doing the contents. And we're grepping for primary MPS. And so we're getting this primary MPS data, but it doesn't really make any sense. It's basically just kind of garbage to us right now. By itself, the data is not really useful, but we don't know where the data is coming from. So once we included this prefix hostnames options, this became really, really valuable. So the exact same query, prefixing the hostname of the machine that we found this from on every single line returned. Now when we grep for primary MPS, we can actually see the 10 or 15 different machines that this line is being queried from. And where this gets powerful is, let's say I want to look for the Apache process. So if I search for the process table, grep for HTTP, all I have to do is basically count the number of times that my hostname pops up, and that gives me an easy way of counting how many Apache processes are on per machine. And that's exactly what this example here is showing. We're searching the process table, we're grepping for Apache, and now we see this machine that has 10 running Apache processes. So just combining some seds, awks, sorts, uniques, counts, now we can get the number of Apache processes per machine in the entire data center sorted. So now this tools of 3 machine is our busiest web server in a specific data center. So the idea here is try to provide as much raw information as possible, and you're not really going to know what your questions you're going to have in the future, but just putting this data out there, hopefully people start wondering what exists in the cache and what you can get out of it. So here's another example. We want to look for hardware failures on a specific application running at LinkedIn. So we can extract sysops cache. I'm looking for active hardware failures. Range queries, basically how we do an application or service lookup. Display the contents, prefix the host names, and it says, okay, this machine app 3145 found a smart hard failure, a disk failure. So this is basically how we query the state of our infrastructure. Another example is show me all the size of the physical disks for an entire group of machines. So here I'm reporting back the exact size in megabytes of every installed physical disk on every machine in the data center. Another example, so security is going to want to know what machines have a connection to this machine salt01.prod. Well, we include the netstat table in here. So every 30 minutes, every machine at LinkedIn is populating netstat-an into this cache. Well, we can grep for a single IP address out of this and see every single machine at LinkedIn connecting to this box. This is really, as far as security, this has a lot of implications. Now security can scan this cache and the network connections and see who's making public IP connections. Is there a botnet running? What are our machines connected to? So there's a lot of implications behind this. So use Red Hat's SOS report or Sun's Explorer as kind of a basis for what you should put into the cache. So Sun, Oracle, whatever you call it now, Red Hat, they build these data collection utilities to basically try to capture a snapshot of the machine because they have no idea what's broken about your box. They're just trying to gather as much information as possible. But these utilities capture everything that you could possibly think of: process tables, mount tables, packages, kernel modules, memory usage. And once all of this data is into the cache, you can really start answering any question you have. The more data you add into the cache, the more your company starts searching against the cache, they realize what's in there, the more useful this becomes. So this will be open source. I'm in the process with LinkedIn now, going through the open sourcing process. But if you are interested in looking at this code, just let me know and we can get that. But right now I don't have a GitHub URL for this. you guys have any questions? I know this was pretty fast. But.
Mike, maybe I could ask you, what is the most common query that you make about your service in the environment?
So one thing that SRE finds pretty useful is our installed package space. So for example, we're managing and we're pushing CFEngine upgrades all the time for package installations. And they want to confirm that their software is on their end nodes or an automation request was completed. So that's kind of how this utility is being used. It's audit our environment before a change happens, use CFEngine to execute a change, and then this is the way for the company to verify that the change was successful. But what the most common query is, it's kind of a hard question because it's what we do every day, right? Every day it's a different question. It's, you know, where do I have hung mounts, or where do I have disk failure? I mean, it's kind of a hard question to ask because we're just, every day is a different question. So.
And does the CFEngine agent help you to repair those things automatically, or are you pretty much involved in manual operations on top of that?
So we have a simple policy, and in this policy all we call is link from. So we basically just have a bunch of link from promises that put symbolic links into the directory. Removing the symbolic link from this directory removes the object from the cache. So it's very simple. People don't even really need to be in CFEngine policy. If you just did a symlink into this directory, all of a sudden data appears in the cache. This was kind of a carryover from when we were using rsync. So rsync actually had to kind of track file objects, and we migrated to this system, but we just kind of left that the same process. So, but yeah, we use CFEngine. If we get a request, for example, we have a bunch of new Fusion IO cards, and we need to query the health status from all of our Fusion IO cards. We would push a CFEngine change to say, okay, execute FIO status now, and drop this into the cache. So this is how CFEngine works in conjunction with this. We use automation to determine what is going to exist in the cache or what's removed from it. So I hope that answers your question.
Thanks. How have you publicized this among your customers?
So Greg is one of our SREs at LinkedIn. The best way I've tried to publicize this is I get quite a bit of questions on IRC, trying to answer some sort of question. And the best way to try to evangelize this tool is just saying, okay, you have a question, here, I answer it in 10 seconds, here's the command I used. So by showing the other operations folks, they have a question, they don't know how to answer it at large scale. You show them the example, you try to write documentation and wiki pages and point them, and it's like, you can try to lead a horse to water and hope it drinks, sorry. But that's pretty much what we've tried to do is, and even within my own group, they're still asking me, you know, perform a cache extraction for this. I don't really understand how this data exists in the cache. And that's kind of the one hard thing about this is, for example, the command PSEF, right, the dump the process table, that exists in the cache as the phrase processes. Well, unless you were regularly using this, you wouldn't know that. So part of the learning curve to this utility is learning what commands are being executed and what exists in the cache. Maybe we need some more documentation behind that, so there's an easy place for people to say, oh, Fusion IO cards, I need to look for FIO status or something like that. I hope that answers your question.
I was wondering, are you doing any automatic anomaly detection on this type of data?
So, we're not. We don't do any server-side replication. When our client inserts data into our 4 policy servers, we have some logic within a script when that happens to basically confirm that its keys were inserted on all 4 policy servers. But that's basically where the replication ends. We probably could put a lot more monitoring around the policy servers themselves to make sure their keys were consistent across all of their friends, but we haven't done that yet.
But are you dependent on asking the right type of questions to the system to understand what it's broken?
I'm not sure I understand the question.
So how do you get an alarm? Can you get an alarm going off as
So yeah, like you're basically saying, could we tie monitoring or alerting into this?
Right.
This is how we detect hardware failure. So every hour at CFEngine, there's machines executing a Python script, and let's say they detect MD atom failure. We basically create a JSON object, we insert it into this cache, and every 15 minutes there's one machine just looking for new hardware failure objects. And when that happens, we interface with Jira, we open up the data center text ticket, and our data center techs automatically get a work request. They swap the disk out, the repair happens, and then the ticket automatically closes because this object disappears from the cache. So we've gotten quite sophisticated with hardware failure detection and repairs to the point where it's tracked all in our Jira ticketing system, but there's no human intervention even involved other than human replacing the hard drive. So, I hope that answers.
All right. Thank you, Mike, very much for a brilliant talk.